All right, welcome back to another video. Here we'll talk about the derivative for inverse trigonometric functions. So what do those look like? Well, something like sine minus 1. It's not minus 1, that's inverse. So sine inverse of x. And its derivative is the following. Then we have cos inverse x has this derivative. I will go through the derivation for the inverse of sine, its derivative, and then you can do similar derivations for the other ones. But let me just list these ones here so that we have them off the bat, and you can refer to them later in the video. Also, I should mention that when you see sine minus 1 or sine inverse of x, you can often also see it as arc sine of x. Here's the notation with arc sine and arc cosine. Let's talk about the derivative for the inverse of tan, which is as follows, and the derivative for the inverse of cotan. They look similar. I try to pair them up with how they look similar to each other. The sine and the cosine differed by a negative sign. As you can see here, the tan and the cotan inverse also the same. Secant inverse and cosecant inverse are a little bit more dangerous looking. Although I don't derive them in the video, their derivation does follow closely with what I do for the inverse of sine derivative. So here's that derivation. We'll talk about setting this up using implicit differentiation. The first thing that I'll do is write down the function as sine inverse of x. Then let's write this implicitly as sine of y equals x. Now, when you see sine of something, there's a ratio because SOHCAHTOA, sine, cos, tan, those are ratios relative to a right angle triangle. So that x there is actually x over 1, for example, and we can construct a triangle accordingly. So there's sine. Sine is opposite over hypotenuse, so that 1 is the hypotenuse. You can fill in the blank using the Pythagorean theorem. There it is. I remember seeing this probably my first year of university, and it was kind of just glossed over in the lecture. I was like, whoa, how did they get that derivative? So hopefully I'm doing a good job here recovering some knowledge that may have been forgotten along the way. Anyway, now let's take the derivative of sine y equals x. This is an implicit differentiation, and I do have a video to that. It probably is one of the previous 1 or 2 videos in the playlist. I might toss up a link in the description later. So the derivative of sine is cos, but since y is implicitly a function of x, we put a chain rule there, dy dx. I'm using the Leibniz notation, as you can see. And then the derivative of x on the other side is just 1. Let's solve for dy dx, which is the reciprocal of cosine. You could also write that as secant. Now, what do you do with that? Well, you need to get that in terms of x so that we can have the derivation complete. And that's easy enough. When you look at the triangle, you'll see that we have cos, which is adjacent over hypotenuse. So it's that root over 1. So we have 1 over that, root over 1. So it's the reciprocal of this, which simply becomes what we achieved. And that's about it for the derivation. So let's do some examples practicing this out. The key difference here will be that a chain rule will be involved since the most basic of derivatives are essentially what were described in the beginning of the video. Here's our first example. We have inverse sine of 2x plus 5. So the pattern there, you can see on the side here, I've written down the rule, including the chain step. So we have here sine inverse of something, u, for example. It's going to be 1 over root 1 minus u squared. So it's 1 over, there's that template, 1 minus something squared. Well, that something is 2x plus 5. We still have to apply the chain rule. So the derivative of that u, or 2x plus 5, is equal to 2. And we can write this more compact as a single fraction. There you go. So if you were good with that one, then essentially we'll be playing this out a few more times. And one last example that has a few 3 or 4 layers of chain rule involved. Something more for entertainment, probably less likely to see in practice anyway. Here's our next example. We have the inverse tan of a polynomial here, a quadratic quantity. So the inverse of tan has a template, which is 1 over that quantity squared. So there you go. Fill that template in with the quadratic terms. And then let's do that chain rule. So the derivative of 7x squared plus 3x plus 1 is 14x plus 3. And we can write that as a single fraction and call it a day on this question. So let's take a look at another example here. This time we have the inverse cosine of an exponential function. We have e to the x minus 8. Now, the inverse of cosine derivative is very similar to the inverse of sine, except there's a negative sign in front of that fraction. So we'll do 1 over, well, negative 1 over root 1 minus that quantity e to the x minus 8 all squared. There it is. And then this is a very friendly chain rule. We have the derivative of e to the x minus 8, which is simply e to the x. And the derivative of 8 is 0, since it's constant. At least you have to do something easy. Let's write that as a single fraction, make it look pretty. There you go. Now, one thing with these single fractions is that negative sign in front of the fraction is often, just kind of forgotten. So I've made, over the years, here and there, I'll forget that negative sign. I'll write it, but then I won't write it down the next step because it kind of falls in line with a fraction. Hopefully, you don't fall into that trap. Okay, here's another one. Now, whoa, this one has a root in it. So you might think that this is actually a tougher question. But if you recall, the derivative of the inverse of sine has a squared in the denominator. See that u squared in the denominator? So you're going to square a square root. So they're going to neutralize each other. And that's actually going to be a good thing. So let's take a look here. We have here 1 over 1 minus something squared in the square root. And that quantity u is the square root of x minus 5. Here you go. And the derivative of that, we had a pattern for that in an earlier video. So I wrote it down on the side here in red. It's 1 over 2 root u. And we also have to do a second chain step here, which is the derivative of whatever's in the root. So that radicand, x squared minus 5, has a derivative of 2x. Those 2's cancel. See them? And then also the root and the squared cancel. So you get a little bit of cleanup here. You could leave it like this, but I'll just write it as a single fraction because it's fine. Also, I simplify the radical on the first denominator. I don't see a benefit to expanding it further unless you're going to try to do some other interesting stuff involving graphing or finding critical values. Anyway, there's your answer. Let's move on to one final example. Okay, so this one here has a hyperbolic sine function embedded within an inverse trigonometric function, arctan of x, arctan of u, for example, actually. And then we have an exponential function, not of base e, which is base 8. And then the exponent is also not just x, it's 3x. So there's several chain rule steps involved here, but let's take it down piece by piece and then move on with our lives because that's enough of these functions. Okay, so there's the inverse of tan. Its derivative is just 1 over that quantity squared. So 1 over that hyperbolic sine function squared. Tuck it in there nicely. And now we have to do the derivative of hyperbolic sine. We had a video on that earlier as well. The derivative of hyperbolic sine is hyperbolic cosine. So that's cute. And then we'll do the derivative of 8 to the 3x, which is an exponential function. And we have also a video for that. Again, you can check up on these videos. They're in the playlist. So really, this is kind of like the master level final boss, if you want, of chain rules. Anyway, let's clean that up a little bit, maybe as a single fraction. This is not the only way to present it. You got a logarithm in there. You got a cosine. You got an exponential, coefficients, all kinds of fun business. I would just leave it like that. Anyway, if you're good with this, you should be in good shape doing inverse trigonometric functions. As practice, I would recommend trying to do the derivation for maybe inverse tangent. I wouldn't bother with inverse cosine because it's almost the same as inverse sine. Very similar root function in there. And maybe the reciprocal trigonometric function inverses, maybe just derive like a secant one or something. If you're really keen on seeing it, I can do like a follow-up quick video on that. Thank you very much. I have another one on the horizon in the near future. Hopefully I can get that up and running so that you can practice during the summer. See you later.